Hello? Yeah, am I audible? Sorry, I'm not hearing any sound. What's up? Hello? Hello?
Hello?
Ah,
Hello?
can you hear now?
Yes.
I was unable to hear, ma'am. Sorry.
Uh,
Some technical issue
Shall we
was there.
start now?
Yes, yes. Yes, we can
Okay.
start.
Good evening, all. Now we are going to start our 14th session. I welcome our resource person, Professor Vishnu Namudiri, and all of you to this session. Hand over to Professor Vishnu Namudiri.
Thank you very much, ma'am. So today we are continuing with our discussion yesterday. We were trying to find approximate solutions of roots. The sense that yesterday used bisection method for locating roots, and the bisection method is of course a very good method in the sense that no differentiability such things are actually assumed there, but of course continuity is assumed there, because otherwise the problem is that we cannot expect the root to be present in the interval that we are searching for. We are assuming basically the fact that we can find out 2 points a and b in such a way that the endpoints of interval in such a way that f of a and f of b are differing in sign. So in such a situation, assuming the continuity, we are hoping to for the graph of f of x to cross the x-axis, where we can locate the root of that function. Okay, so continuity is essentially assumed there. Even though we are not stating this thing, even though we are not seeing that continuity is where exactly is being used, it's assumed there. Now, bisection method is comparatively, from the computational point of view, seems to be somewhat time consuming and resource consuming, especially if the routes are at a large distance from wherever we are starting. And already, I think yesterday itself, Professor Taji already pointed out that already she was asking about how to locate actually two starting points A and B. And I told that determining two starting points is more or less it's something like arbitrary, because we need to just look at the graph of that. We need to just check A and B. We need to find out A and B in such a way that f of A and f of B are differing in sign, and in that case only we can actually start with attempting to bisect the interval into smaller pieces and locate the root in that way. Now we are going to suggest another method, which is actually assuming a little bit more stronger condition than continuity, differentiability. Newton-Raphson method we are going to use for finding approximate roots of an equation. And equation in the sense that not necessarily polynomial equation, it can be some other equation also, doesn't matter. The only thing is that it must be differentiable. And from the computational point of view, once again, Newton-Raphson method seems to be somewhat more efficient compared to a bisection method. Okay. After discussing Newton-Raphson method, we will go into solving systems of equations using. Already we know that we have a solve command available in Python, in symbolic Python actually. But instead of that, we will try to see how the Gaussian elimination method work in finding out the system of solutions and finding out the inverses also simultaneously. Inverses provided that the system is a system actually gives you a square matrix. So initially we will try to see the Newton-Raphson method for solving system of solving equations. Okay, let me start sharing my screen. So the Google Sheet where I'm going to paste the Python code is here. So we are into our 61 program, Newton-Raphson method. So as I told, so what we are trying to do is that, of course, even here we are supposed to start with some approximate solution, but the thing is that it need not be a closed solution or anything like that. We can start somewhere. Okay, after that we can proceed to the actual solution. So the main formula that we are going to use is this. I'll just try to show you the formula first. The formula that we are going to use is our iterations are something going to be something like this. So we start with an arbitrary solution. Okay, we are determining that some number we are choosing and need not be very close to the actual number, need not be very close to the solution because we don't know the solution. And let us try to see the number of steps we are taking if we are choosing a wrong initial approximation. So this initial value that we are choosing, suppose that we call it to be the initial approximation. Okay, and suppose that it is xi. So now xi plus 1, how do we choose? So xi plus 1, provided that xi is known to us, xi plus 1, now the equation we have to solve is nothing but f of x equal to 0 and f is differentiable. So in the case of numerical analysis, we'll be making some vague statements like if is differentiable. In the case of real analysis, you may probably ask that if is differentiable where. So in this particular case, you just assume that if it's differentiable wherever we want. That's it. We cannot say anything else because the equation that we're trying to solve is supposed to be well behaving in the interval where we are going to do all these computations. So xi plus 1, according to our computational formula for the Newton's Raphson method, it's equal to xi minus fx by f dash x. F of x by f dash of x. Oh, f dash of x, what we mean is xi. So this is the computation formula that we are going to use, essentially. So when do we stop? We will stop at one point when we are getting f of x to be f of xi to be very close to 0. Exactly the same method, exactly the same way in which we checked whether something is a solution in the case of bisection method. So xi plus 1, we will keep on finding xi plus 1. Initially, we will assume xi or x1 to be something. After that, we will find x2. After that, we keep on finding solutions like that. And of course, there is a danger that we will never converge and we will enter into an infinite loop. Let us see if that's happening later. So after finding xi plus 1, xi plus 2, xi plus 3, etc., we will check f of that particular value every time. If it's less than epsilon, we actually want that value to be equal to 0, but provided that it becomes less than epsilon, we will stop as accepting that to be the approximate solution. That's what we are going to do. So in each and every step, we need to compute this previous solution minus f of previous solution by f dash of previous solution, and that value we will take as the next approximate solution. This is the technique that we are going to use. Okay. So let us try to do that. Let us take a polynomial. For the sake of understanding, let us take a simple polynomial. Suppose that we call y to be equal to, instead of f, let us write it to be equal to y. Okay, we need symbol because we want to differentiate from sympy, import symbol, and the derivative name was derivative. So two of them imported. Let us try to find x square minus 2 so that an approximate solution is going to be equal to square root of 2. So y is equal to x square minus 2. This is, oh sorry, this is latex. Confused. X square minus 2. And in this case, we know that the solution is going to be something between 1 and 2 because the square root of 4 is 2, square root of 1 is 1. Therefore, it must be between 1 and 2. So we can maybe we can start with 1. So let us take the initial solution to be equal to 1. Suppose we call it to be not x. What should we call? C. Suppose we call that to be equal to C. C equal to 1. Let us take the initial solution, initial approximation to be equal to 1. I'm just choosing it like that. Later we can try to modify this, change this into something else, and after that we will try to see if the number of iterations are increasing, decreasing, etc., depending upon our choice of the first or initial approximation. C is equal to 1. Now we should define an acceptable bound also, so that we can stop after that. Once that f of x becomes very close to 0, we will stop. So let us choose epsilon to be something like 0.05. Now what do? We need to check y substituted, instead of x put c, while this is less than, sorry, this is greater than epsilon, we are going to do the following. Okay, so y substituted xc means that we are substituting of in the at the value of at the place of x we are substituting c in y. Therefore, we'll get c square minus 2. Okay, so now we need to go for the next value. So c is equal to the previous value itself is c. Remember that in programming, what happens is that the right side is computed first and it is stored to the left side variable. So we can safely use c is equal to c minus. So f of c divided by, now we require derivative. Okay, let us find the derivative also. Df, let us call it as df. Df is derivative of y with respect to x. So df, let us substitute x for x c. The computation goes on. Let us try to see the value of the c substituted to x. That's it. Now, towards the end, once again, we need to print. And let us see, let us try to find c also. So let us print c also. And maybe in each and every step, we can actually, okay, okay, I'll try to show that later. Okay, this is what we are trying to do. Let us save this. Saving, running. Okay, x equal to symbol x. One and minus one. Why is it like that? When we are substituting c to this, what happens is 1 minus 2. Okay, we need to go with the absolute value. Sorry, that's very important. Absolute value we should use, because otherwise the problem is that it's negative. Now let's try. F is not defined. Where is this f? Oh, once again the same kind of mistake. This is f of c. F of c is nothing but y substituted with c. Running. Cannot be truth value. What happened here? Y substituted this absolute value. I think abs is coming from math, right? So I don't know. Abs is actually, let me just print abs minus 1 to see if abs is coming from the math module or not. No, abs is not. So absolute value, here it is. Absolute value of y substituted at the place of x we are substituting c. While absolute value of this is greater than epsilon, this should be tried. And why is it giving the error like this? Cannot determine. Okay, let us see where it is, where the error is. Absolute value of y x c. What's the problem here? I don't see any problem here. While absolute value of y substitute, oh, subs is not imported. Oh, subs. Oh, but I think subs is not necessary to be imported. Okay, let me just see once. Let us print it here. Is subs the problem? No, that's not necessary. Cannot determine truth value of relation. What's by that? Just 1 second. It's a sympy error. Okay, let me just see. Something is happening here. Okay, that's a typical error with sympy. It seems okay. I will do one thing. If okay, I'm just trying. If the problem is in comparison, I'm just trying to see what exactly is happening here. Still, it's wrong. Cannot determine truth value of relational. Let us try to see print error. What is the value of that error? Absolute value of, oh, I think it's because absolute value of 1 plus 1 subs derivative. But where is that happening? 1 plus, oh, in the second step probably it's happening. 1 plus derivative y of x, derivative with respect to y. Sorry, I forgot to do one thing. So yeah, that's the mistake. Do it was missing. Okay, exactly. Oh, sorry, I completely missed that. So this is not really necessary. The problem is not here. So the derivative is just giving an object kind of thing. It is not actually a number. For evaluating that the number, we should apply. We should have applied. Do it. That I did it. While this is greater than. Okay. Now this should be fine. So what are the values that we are getting? C, and maybe we can convert this into numerical value. So for even converting, I think I will put it as 1.0. Okay, that's better because otherwise it's always trying to put that as a fraction. So the values that we are getting are 1.0 and minus 1 as f of c. After that we are getting uh, okay, let us try to see here 1.5 and 0.25. So 1.5 as the value of c and 0.25 as the value of f of c. So still it is greater than 0.05. Next value we are getting to be 1.4166 and 0.069. Okay, so in the third step we are getting the final answer. So we have taken third steps to complete. Now if we take, suppose that we start with 10, what will happen? So number of iterations are increasing. Number of iterations are further increasing, but still it's converging. Minus 100. Same. It's still conversing. Okay. So let me update approximate solution is, and f of this value is, I'm just printing it in somewhat neat format C, C, and this. Approximate solution is 1.41, etc., and f of that value is this. Okay, let me update the Google document with this. So the Google document is updated with this. Now, if you want to see the roots plotted, maybe we can even do that. So in action, let us try to see this in action by plotting it, so that we can understand what exactly is happening. Import matplotlib pyplot as plt. Just trying to do maybe import numpy as np. So this is not actually part of Newton-Raphson method. We are just trying to understand what exactly is happening by plotting it. Plt plot. So what should we plot? X square minus 2 we should plot. The curve we should plot x square minus 2 y is equal to x square minus 2 for plotting. The only thing is that we need to choose x values, x data or x points. X points, let us choose x points in the range. Since the root is somewhere near, what is the root? 1.4. Let us take it in the interval 0, 3. So NP linear space 0 to 3, say 100 points are taken. Y points is x square minus 2 we need. So we can just take x points square. I don't know whether this will work. Let us try that. Try to see that. Print y points. So what are the points we are getting here? The initial point is minus 2. Minus 2 is nothing but because we have taken 0 here. 0 square minus 2. That's fine. I think yes, we are getting it. So x points and y points are here. Now trying to plot x points, y points, and plt show. So let us suppress this. So this is what we are getting. This is what we are getting here. This is the curve. So part of the parabola essentially. Now, if we try to plot the points also that we get, that means that c and y substituted to that c. Suppose we plot that also. Let us defer the plotting to a later stage. Keeping on plotting, PLT, plot. Uh, Plotting just 2 points, these 2 points. Will it work? I don't know. We may have to see. Maybe we can put some color change also. R, O. So these are the points. Suppose that, okay, where did we start? Let's suppose that we start at, if you use -100, then it's going to be too far. So maybe suppose that we take 20 and take 200 points, still fine. Take it as 15. So we are getting this many points. And the final one, let us put in a green dot. The final solution, let us put as a green diamond. So the final solution is here. The final solution is here. Maybe the legend also we can, okay, legend we cannot turn on so easily because we have too many plots here. Okay, anyway, otherwise, so the solution we are starting from here, we can say that the solution is it's taking a huge leap from that 15, it's coming to 7.5 directly. After that, it's slowing down to somewhere near 4, it seems, and after that, it's becoming below 2.5. Then it's further below, and it's very close to the final answer. Okay, this is how it's working. Okay, we can see that the distance is slowly, it's slowly converging along this line. It's slowly converging along this line. Okay, so this is zero. This is zero, and this green dot is against zero. Let me just update the Google Sheet with this, the complete program. Update. I think this program is quite simple and very easy to understand. It's not at all complicated, and it's comparatively, I think, less time taking compared to less number of steps are taken compared to the bisection method. Of course, we can instead of this polynomial function, we can try to do with the exponential function or any other function. The program is exactly the same. For example, suppose that we define import exponential, and suppose we define exponential of x square. Exponential of is not going to be equal to 1. So e of, let's change this function to something else. Exponential, instead of x square, let us take 2x or 3 e raised to 2x minus 2. Oh, 3 star, sorry. It's almost like a straight line. Because this is because here we have taken the straight line. x points minus. So maybe we need to use list comprehension here instead of that. So let us use list comprehension instead of that, so that we can plot the graph of this function also smoothly. So y subs x a or a in x points. Let's use this. The range we have chosen is too large. Let's take the range to be something of the form 3 and start with 2.5, say. -1. Yeah, root is coming down like this. Starting from here, I'm updating. I think I will update this as a separate program. So it's the same program actually. I'm updating it as a separate program in the Google document, so that you can try with this also. There are a few changes made here and there, so I'm just keeping it as a separate. So the Google document is updated. Okay, so that's it with the Newton-Raphson method. Now, as we have discussed, now, as I said in the beginning, we are now going towards discussing the Gaussian elimination method for solving system of equations. And yeah, before even going further, I'd like to say one more thing: that for finding the solutions, actually, we don't have to do any of these things. We are doing all these things to understand how exactly to find out how exact. Yeah, is that a question?
Sir, after correcting the errors, how to refresh the window? Hello?
I don't understand. What do you mean by refreshing the window?
If the error comes means then we will correct now. Then after this how to run? Again and again the window is showing error.
Where in Google Colab?
Spider.
In your window.
Sir,
In you are trying in your spider in your machine.
spider sheet.
No, what I'm asking is, are you trying to do? Are you doing the programming in your spider program now?
Yes, sir.
What is the error? What is the error appearing there? What kind of message you are getting?
Indentation error.
Indentation error.
Indentation match any outer indentation level.
So it's happening at which line? So it must be giving one line also. One print cy substitute. Which line is happening?
Yes. Yes, yes.
In the first line, print cy substitute.
Then the approximate solution is format C, comma C, comma Y dot substitute X, comma Y.
You please do one thing, that final print line, you please move it towards the left so that it will be close to the margin
Okay, sir.
by deleting some space, because indentation error essentially means that there is some unwanted space.
Yes, thank you, sir.
Okay, now I wanted to just show that instead of doing all these things, there is actually a method given by symbolic Python for finding the roots directly. From sympy, import, I think, roots. So print Can you please mute? Okay, thank you. This is y. If you try for roots of y, let us see. The roots we are getting to be square root. Okay, let us try to find the approximate solution. Oh, but sorry, you are not going to get the approximate solution like this. Here you are getting the roots to be square root of 6 by 3. Not exactly. So what are the solutions that we are getting? The square root of 6 by 3, 1. Square root of 6 by 3, 1. So 1 essentially means that it's, okay, let us try to do with something familiar to us, x square minus 2. Square root of 2 1, square root of 2 1. So what is meant by square root of this is a minus square root, sorry. This essentially means that minus square root of 2 is appearing one times, it's multiplicity. Okay, so there are multiple roots possible. For example, if you have x minus 1 the whole square, then 1 is a multiple root. Here minus square root of 2 is appearing once, square root of 2 is appearing once, because x square minus 2 there are two solutions. Now if you want to get the numerical value of these things, what you have to do is for s in roots of y, print getting the numerical approximation. So you will get the solution to be minus 1.414 and 1.414. See that previously by Newton-Raphson method we got solution to be 1.43. Okay, here we are getting 1.414. So this roots function can be used for finding out the root directly. But why we are discussing the Newton-Raphson method is that, so we are trying to understand certain methods. We are trying to understand how Python programming language can be employed for solving our problems. Not all problems that we have will be solved by Python in its own. We may have to write our own code for solving certain other problems. So if we try to understand how to write programs, then we can make use of the experience that we are learning from this writing code into in that particular situation where there is no ready-made, readily available function like roots is available. Okay, that's the only thing. So Python method or sympy function for finding roots. Print roots. So you will get a dictionary of roots. Sorry, print roots of y. We'll get a dictionary here with multiplicity. If you want to get the approximate, if you want to get the numerical values, then numeric values are okay. I will update the Google Sheet with this also, so that if you want to have it, if you want to try this, you can even try this. Okay, I have updated. Okay, now we have almost completed the discussion on finding roots of equations. So we discussed two methods. One is bisection method that can be used on any function which is continuous. Second one is the Newton-Raphson method, which can work only on differentiable functions. And this roots command, I don't know on what type of functions it will work. Most probably it will work only on the functions that sympy actually defines. So if you are defining a function which is not given by sympy, then that's not probably going to work. On user-defined functions, probably this, of course, on polynomials also this will work, because polynomial is something actually defined by something actually given by sympy. But if you define your own fancier functions, then roots, I don't know exactly whether it will work or not. You may have to try and see. Okay, I'm just moving to the next program, starting a new program. So this is Gaussian elimination for solving system of equations. And we know that if you have a system of equations, and if that system gives you a square system, in the sense that number of variables equal to number of equations and the coefficient matrix is invertible, then by inverting the matrix you can find the solution. That's one way. But if the system is not like that, if number of variables is not equal to number of variables is not equal to number of equations, or if the matrix that we are getting, the coefficient matrix is not invertible, then that method is not going to work. In such a situation, we need to use Gaussian elimination for finding the solutions. Even for determining if the system is consistent or not, we need to probably use that. Of course, by checking the determinant, if it's equal to zero, by checking the number of equations is equal to number of solutions, in that way also we can determine if it's consistent. Okay, but still, for finding out solutions in case of inconsistent systems or non-unique solutions, we need to definitely use this. Okay, suppose that we have an equation to solve. Let us take some example and try to understand. So I'm just using one equation available from a book called Python for Scientific Programming, Python for Numerical. Sorry, I forgot the name of that. Numerical Methods in Python. So that's the book name that I'm using right now. I'm copying and pasting the equations from that so that some typing can actually be saved. So this is the system that we are trying to solve. So 2x1, 4x2, 2x3, 4x3, so 2x3, x1. So this is the system we are trying to solve. So program number 62. Gaussian elimination.py. So to solve the system in Gaussian elimination, what happens is we will try to convert this into a kind of upper triangular or upper triangle essentially, because what we usually do is we will check which equation among the given equations has the x1 coefficient non-zero. Okay, so we bring that equation to the top by interchanging the equations, interchanging the rows essentially. After interchanging the rows, what we do is we will try to make the solutions below the top equation. We will try to convert the coefficients of those two equations in such a way that the x1 coefficient is 0. So the coefficient of x1 will be non-zero only for the first equation. Using the similar technique, we will try to make the coefficient of x2. We will leave the coefficient of x2 in the second equation without making any change, or we can make, of course, convert it into coefficient equal to 1. In some techniques, we convert that coefficient to be equal to 1. That's also possible. And after that, in the first equation and third equation, we will try to make the coefficient of x2 equal to 0. So x1 coefficient is non-zero only in the first equation, x2 coefficient non-zero only in the second equation. And in the third equation, x1 coefficient as well as x2 coefficient is 0. Only the coefficient of x3 possibly is non-zero. So in such a situation, we are getting an upper triangular matrix. So if you write the coefficient matrix into the variable matrix, we will be getting a matrix into x1, x2, x3 as the column matrix. On the right side, 11 minus 16, 7. Okay, we need to make changes to this. Okay, I forgot to tell one thing, that we need to form the augmented matrix first, which means that the coefficient matrix, and together with that, the last column, we augment this 11 minus 16, 17. We'll make the same changes to this 11 minus 16, 17 also. So finally, we will get the last equation will be having only one variable. So we will solve for the last variable, x3. We will substitute this x3 into the second one. So we will get x2. We will substitute this x2 and x3 into the first one. So we will get x1 also. So backward substitution. This is essentially the philosophy, the logic behind Gaussian elimination. But in several variations of this equation, this elimination, what happens is, sometimes we will convert x3 coefficient in all other equations 0 other than the third equation, x2 coefficient in all other equations other than second equation 0, x1 coefficient, and also the leading coefficient, we call that to be the leading coefficient. That is the coefficient of x1 in the first one to be equal to 1, coefficient of x2 in the second one to be equal to 1, coefficient of x3 in the third one to be equal to 1, so that we'll be directly getting the solution. Okay, we'll be directly getting the solution. This is the essentially the logic behind that. So initially we will try to solve this concrete system, and after that we will try to see how to generalize this method for solving any system of equations. Okay, so let me just comment out this. Sorry, commenting out. Okay, so the equations are commented out. So here, remember that we need the augmented matrix. Okay, so for getting the augmented matrix, basically what we can do is that, okay, we can either leave the okay, 11 minus 16 7. Okay, we will take that also into our matrix system. So we will form the augmented matrix. Let us call that to be uh, AB. So the augmented matrix is, we need to form a matrix. Import numpy as np. So np array we are going to form. So we need to form lists of lists. So the first row is going to be 4 minus 2 1, and the second row is going to be, okay, 11 is also there, 11. Second row is going to be minus 2 4 minus 2 minus 16, and the third row is 1 minus 2 4 17. This is the augmented matrix. Trying to see it in action to see what it is. Four minus 2 1 11, minus 2 4 minus 2 16, minus 2 4 minus 2 minus 16, yes, 1 minus 2 4 70. That's fine. So what is the first thing that we have to do? We have to change, we have to modify. If you prefer to make the coefficient of, see that x1 in the first equation has non-zero coefficient. So there is no need of interchanging the rows as of now. So let us see that in the later stages, it may happen that the variables may be having in the second equation also, the coefficient of x2 may become equal to 0. In that case, we may require interchanging of rows. As of now, it's not required. Now, the first thing that we have to do is that the first row, if you want to convert, if you want to change the coefficient of x1 to 4, okay, if you want to if you want to change the coefficient of x1 to 1, so what do we need is we need to divide the entire first row with 4. Okay, maybe we can even do that. Or otherwise, we can just, okay, maybe that can be done even uh, in the last stage. Okay, let us try to eliminate it first. Try to make um, one variable in each row with one variable in each row, and the the variables before that, the coefficients before that, to be equal to 0. So we will leave 4 minus 2 1 11 exactly like that. And the second row, what we will do is that we will try to make the coefficient of x1 equal to 0. So for doing that, what do we need is second row should become, so row 2 should become row 2 minus, so what is it? The first row, first element. First row, first element is coefficient. That's so we have taken it as AB. So how do we get that first element? AB. In that, I think 4. Sorry, 0 0. AB 0 0 times. So what do we need? So row 2 minus. So what do we need is row 2. Okay, now you need to be careful. So this is minus 2. Okay, row 2 should become minus 2. We want, okay, otherwise what we can do is that we can convert even that. Let's do that, that's better. Row 1 becomes row 1, that's much more easier, into 1 by 4. Let us make the coefficient to be equal to 1. Let us do that. So this is the first step that we are going to execute. So to do that, what do we need is A, B. Row 1 stands for, the column must be row 1. So this is 0. So, and this one needs to be just this. So every element. Row 1 must become equal to row 1. Which element we should multiply? 0, 0, 1 by that. We need to multiply. So this is the first step. Let us see AB. What is AB is after this? Okay, this has become 1, 0. Maybe we need to be a little bit careful. Why is it happening like that? 1 by AB 0, 0 is nothing but 4. So 4 has become 1. So what we did here? Minus 2 has become, but why did it happen like that? Okay, let us try to see what this is. This is not needed now. This is also not needed. 4 minus 2, 1, 11. 4 minus 2, 1, 11. That's fine. That's the first row. And let us try to see AB 0, 0 also. That is 4. That's also fine. So what is this? That's already printed. So why is it happening like that? AB maybe I will include this in a bracket. It's not probably necessary, but still trying. Oh, what happened here? 1, 0, 0, 2, minus 2, 4, minus 2, 16. That so with which row it's multiplying then? Minus 2, 4, minus 16. So the scalar multiplication is not working as expected. 1 by 4. So this is not correct. So this is also not correct. So this is 11. 11 is turning out to be, I think it's because 11 by 4 is how much? I think it's getting approximated. Okay, let me just try. Because it's probably numerical values are getting. Or maybe otherwise I can straight away use the list comprehension once again. Equal to 1 by this. So let me just use a list instead. 1 by, this is not the problem. Star C or A for A in it was working previously. Why is it not working now? Multiplying scalar. Okay, let me just try to see another way. Maybe I will multiply the entire. This I want. Okay, let me just use this instead. Multiply with this. Will it work? Multiply operator to int forecasting rule same kind. Maybe or let me just try to see with 4. Is it working at least directly? That's surprising. And why is it not coming out to be correct? 4 minus 2, 111. That's perfectly fine. So star 2, that's fine. 1 by 2, that's also fine. So what is the problem then? This is equal to, maybe I can multiply it on the right. Let me try to multiply it on the right. I'm trying this on the right. Let me just see that. AB, which is invalid. Oh, sorry. 2 minus 1, 0, 5. 2 minus 1, 0. I think it's getting approximated somehow. Okay, 1.2.0, maybe 4.0 if I include. Oh, I think that's the problem. Oh, somehow it's a strange behavior that we are having an integer items. It's treating everything as integer. That's somewhat surprising. Somehow that keeping this as a floating value is seeming to solve that problem, but that is actually a strange thing. It should not have. It should not. It shouldn't happen like that because that is highly unexpected. I don't know why it's happening like that. Anyway, this is actually solving the issue at least. So let me just try to see with the multiplication 0 0 and what happens after that. 1 by this star this. That's a strange behavior. star this. Okay, this seems to be anyway working. So okay, let us just take that to be the behavior. I don't know why it's happening like that. 4.0 after giving 4.0, it's working. Otherwise, it's being taken as an integer, and therefore some kind of rounding is happening. It's not expected, but it's happening like that. Okay. Anyway, so we changed the first row, and after that, so this is what we wanted to achieve. Next is row two should become. So what is our row 2? Row 2 now consists of minus 2. We want this minus 2 to become 0. So for that, we need to multiply this 1 with minus of this and add it. Okay. So row 2 plus minus of the first entry in row 2. Minus of the first entry in row 2 is nothing but that is 1 0. Okay. That's 1 0. Minus of the first entry in this one, 1 0. Now plus row 2. Row 2 is nothing but this is what we want. Now coding it. This is the first row. First row in the sense that zeroth row is the first row and row number 1 is second. So row 2 plus. So this plus. Or we can straight away even write something like star equal to instead of doing all this. And here plus add to it. So what to add? This minus value. Star this. Let us see AB. So AB is becoming like this now. Here again, is there any problem like what we have faced previously? So 4x2, it is multiplied with 4. Sorry, 4x2 was multiplied. Okay, this was, okay, we should see the row first. Let's see this in print. After each and every execution, let us see this in action. So this is now multiplied with minus 2. Therefore, this has become, this is now minus multiplied with a minus of minus 2, which is 2. 2 into minus 0.5, which is minus 1. Minus 1 plus 4. So we are getting it to be equal to 3. So seems to be correct. Now the same thing we need to do for the other rows. Row 3 also we should exactly do the same thing. So row 2 becomes exactly the same. No, 2. So that's it. So we have got this much. Now, in the next step, what we have to do is that we have to eliminate the minus 0.5 and minus 1.5, leaving this 3. And of course, we need to multiply this entire row with 1 by 3 so that this will become equal to 1. Okay, now the same procedure we are going to repeat. So this is the next procedure that we are going to see. Let us try to automate it afterwards. So now, the first row should become 1 by, this is the second element. Sorry, 1 0. Seeing it. 1 0. No, it's 1 1. So this was 3, became 1, 1.5 became 0.5. Yeah, that's fine. Now the next step is that we need to eliminate 0. Minus 0.5 and 1 point. We need to convert this row in such a way that this the minus 0.5 and minus 1.5 becomes equal to 0. So for that, we need to exactly the same procedure that we followed in the previous step. We need to follow here. So which is that row? This is the 0th row. So AB, which element we should add? Not 1 0, the second element, which is 1 1. So what is required? Row 1 should become row 1 plus minus. Okay, how many times we require? We need to add this zero, not zero. So what is the next step required? So we need to remove this minus 0.5. For that, we need to multiply the second row, or the second row with a minus 0.5, which is the second row. Second row is this minus 0 point minus of minus 0.5, because this is not, this is 0 1. Okay, so the same procedure but for row 2. So we need to multiply minus of not 2. So what do we did here? So what is essentially we want a row 2 should become, okay, we just write row 1 should become row 1 plus 0.5 times row 2. This is what we want. So this is row 1. This is this already plus is already here. Minus 0.5 minus of minus 0.5. That's minus of AB01. Okay. Now in the next step we require row 3 should become row 3 plus not 0.5, but instead of that 1.5. 1.5 row 3. So row 3 is, so this is 1. This is 1. Absolute value of not 0 1 but 2 1. Okay, let us see everything in action. 0 1 0 1 0. Now the last step remaining is to just make this one 0. So only this one we want to make it to 1. So absolute value of 2, not 1 1 but 2 2. So 1 0 0 0 1 minus 0.5 0 0 1. Now we need to convert this and this into 0. This is already 0, but still we will write the code, because it can always happen that that's non-zero if you are taking a different equation. So let's do that once again. The same change. So row 1, initially dealing with row 1. So this is not 0 1, but instead of that 0 2 we require. Get the second row. Second row. This is first row. Which element we should multiply? This is the 2 1. Yeah, that's the first row, no, sorry, the second row should become a second row plus 0.5 times third row. 0.5 times 0.5 is nothing but it is 1 2 third row. Let's see if this is correct. So 1 0 0 0 1 0 0 0 1. Solution is therefore 1 minus 2 3. 1 minus 2, 3. Okay, let me update the entire Google document with this code. After that, we will try to see how to generalize this. So this solution is going to work for this particular technique is going to work for any 3 by 3 matrix. But what we are trying to see is how to see here we have manually found out that what to add, what to not to add. We can do it in a loop. Instead of doing all these things manually, we can do all these things in a loop. Just updating the Google document. Update. Please try. Okay, now the thing is that we need to check, we need to do this program in full generality. So let me copy and paste the entire code, and I will try to write this entire code. See, we have executed the same kind of code, the same type of code multiple times we have executed, but instead of that, let us try to do it in a loop. So let me just copy and paste and call this as Gaussian elimination general. So more or less the same code, but the only thing is that the program is for a general matrix, not exactly for 3 by 3 Gaussian elimination general. So let us keep the same equation. Or what I'm wondering here is that if we change this to, if we define, instead of writing it like this, suppose we write NP array, and can we apply float directly to all these? Sorry, that's not possible. Okay. Now trying to write the general program. So while writing the general program, what are the essential things that we have to check? The one important thing is that how many times we need to iterate. That's one thing that we need to check. Okay. So if we have, suppose that we have some, it's an n by n coefficient matrix. Suppose not necessarily m by n. It's going to be so depending upon each and every row, we want to convert. We want to convert each and every row to contain one element with a leading coefficient equal to 1, and the other elements before that to have coefficient equal to 1. So the number of what you call elements we want to find, number of iterations, number of conversions we want to make is actually equal to the number of equations. Okay, so a number of equations is one thing that we want to. Why this coloring in this color? Number of equations is one thing that actually we want to. what's happening here? Just 1 second. Gaussian elimination. Let me just delete it and create it once again. No. Okay, trying to make it general. So what I was saying is that the one thing that we need to know is how many rows are actually there or how many equations are actually there. So that we need to essentially count. So how do we count that thing? That's the first thing that we need to understand. Okay. Of course, if we are giving the number of equations, definitely you know. To find the number of arrays, to find the number of rows or columns, what we usually do is a command called shape or array shape. All right, not array shape. To that array, we need to put the command shape. We can find out number of rows and columns. So to find out number of rows and columns, we use AB, the argument matrix, AB dot shape. On printing rows, columns, format rows, columns. Okay, let me just remove this for the time being. So 3 rows and 4 columns are there. So we need to probably repeat this modifying row. We have 3 rows to modify. Therefore, we need to iterate whatever code we have written 3 times. Okay. So for R or I in range 3. So this is what we are going to try to do. Now I am copying and pasting each and everything from here. So what is the first thing that we have to do? The first thing we have to do is that assuming that the first row, the very first element in the first row has leading coefficient equal to, so let us assume that, okay, if we want, we can even check that. So we need to check essentially that if the leading coefficient in the first row is 0 or non-zero. If it's equal to 0, we need to interchange it with probably the second one. Okay, that's the very first thing that we have to do. So the very first thing we have to do is to interchange 2 rows if required. So let us even do that. I think that's better. So if the matrix is already there with us, if AB, so we need to go through each and every row. If AB I 0, so remember that I 0 for the first time it's 0 0 equal to 0. So we need to bring. So what should we do is we need to we need to check, we need to interchange with the second one. If the second one is non-zero, we need to interchange with the third one if the third one is non-zero, and we need to go on like that. So so essentially then okay, we will do one thing. We will so instead of finding out exactly where the non-zero element is going to be, we will simply interchange the 2 rows. Okay, so if you know that the first element in the first row is definitely 0, then the only way left for us is to either interchange it with the second row, or interchange with the third row. So instead of doing that, what we are going to do is we will I don't exactly know the logic that we are going to apply here. I'm just trying. Let us try to do that, and let us try to see if it's working. So if I 0, for the first time, if it's I 0 is equal to 0, we will interchange with I 0 and I plus 1. Okay. So the previous one we are not going to touch anyway. We are not going to interchange. In that case, is that a very safe logic? That's what I'm wondering. If AB I 0 is equal to 0, we need to interchange with the next J. Okay, so we will go into a loop for J in range. So the next row is going to be um, I plus 1. I plus 1, 2, 3. So what is this 3? 3 is actually the number of rows. So let us take this to be rows. So we are going to interchange with the row j. If so, what should we do? Let us assume that at least one row is going to be non-zero. Okay, let's assume that at least one row is non-zero. Not one zero has leading coefficient to be non-zero. If everything is zero, there is nothing to solve. So okay, even otherwise, I think we can postpone for later this particular part, that interchanging the rows. Assume that in each and every row we will be getting a non-zero element. Okay, let us proceed like that, because otherwise the program will become too complicated. So let us try to deal with that particular issue later. That interchanging the rows, if the leading coefficient, if the leading coefficient is zero, interchanging that. If, for example, if the x1 coefficient is zero in the first row itself, interchanging that first row with the second row or third row, we will keep it pending, and after some time we will come back to that. Maybe we'll assume simply that that's not zero. So what is the first step in that case we need to execute? The first step we need to execute is we need to convert the element in that ith row. So in the first row we have to convert, in the first row we need to apply first row. In the first element we should divide the entire row with that particular element. In the second row we need to divide the entire second one with, of course, still the problem is that it can be equally zero, but let us assume for the time being that it's not equal to zero. Second element in the second row is not zero, third element in the third row is not zero. Let us assume that for the time being. After that we will try to do it in generality. So the multiplication is the next thing that we have to do. The multiplication, how should we do? Exactly in this way we should do. So AB, this is I with I, I. So this is what we are supposed to do in the beginning. So after that, what is the next step that we need to follow? The next step is that we need to change the other rows. So for that we need to loop once again. J in range rows once again. But the thing is that you should not touch the row I. And j not equal to I. You should say that clearly. So what should we do? AB, the jth row become uh, j. So this is 1 instead of that j. So what is this? This is I. This is I. We don't have to write this code. This is not necessary. So after these steps, what happens is that, so the first row is divided with 1 by that. The second row has become, the second row and third row, the zeroth element has become equal to 1. Let us see. Okay, after that, what happens? After that, it goes to the second one, the second row. Second row becomes again the same way. So the same procedure is followed. So let us see it in action and see what the output is. I don't know whether this will succeed. I'm just trying. Cannot cast multiply to d type which is casting same kind. So what is happening here? 1.0 absolute value for I in range. Where is this happening? So let me just try to do this first. I in range 1 by AB I. 1 by ABII. What's the problem here? In PII, maybe once again the same kind of problem. So 4.0, let's take. So to solve this issue, J is not defined. For J in range, where is this J being used? J is being used only here, right? For J in range rows and J not equal to I. Okay, maybe is it because of that? I don't know. If J equal to I, so what's happening here? 1 0 0 1 minus 2 3. Perfect. So that's it. So everything that we have done in the previous program, repeating the steps. So we what we did here is that we took I to be equal to 0 first. So the first entry in the first row that we made it into 1. After that, the second row first entry made it into 0. So j in range rows. The problem is that j also will be equal to 0. Okay, in the initial stage, j will be equal to 0, but 0th row we don't want to touch as of now. So we want to start from 2 and 3. So when we are having I equal to 2, we don't want to touch 2 again. So j will be equal to 1 and 3. So that's why we are asking for if j is equal to I, continue. Continue means that not to go down, but continue to this for loop. Go back to take next value of j. So continue essentially means that take the next value of j. After that, the row is being manipulated, so this process continues. And finally, A/B is print. That's it. Let me just update this first. As I told, this is not the completely general program. Let me update the Google Sheet. So update. Now the problem remaining here is that suppose that the first row has first entry instead of 4. Suppose that we have equal to 0. Let me just copy this and creating another program trying to achieve the full generality. Gaussian elimination general 2. It has 64. Now, if you want to achieve the full generality, the thing is that we need to handle the situation that the leading coefficient is equal to 0. So, in such a case, we need to interchange the rows. The interchange rows means that with which row we can interchange. And suppose that no rows are having x1 coefficient to be equal to 0, then what should we do? So such an issue is there, but okay, such an issue is definitely there. Such an issue can actually happen also because even if it's not happening in the first equation, for the second equation can actually happen. That means in the second equation, suppose that we have three equations, and after the first step, suppose that x2 and x3, both the coefficients are becoming zero in these that second and third equations. So at that particular stage, we cannot actually proceed. We need to stop. So if you are not going through the complete the I range, it essentially means that some of the variables we are unable to find, and the system, um, some variables will be able to accept arbitrary values. Okay, so there is no unique solution. That's what essentially it means in such a situation. So we need to handle that situation also. So suppose that we are choosing I, and suppose that the ith row leading coefficient is equal to 0. Then we need to go to the next row and see if the same coefficient, that ith coefficient, is equal to the next row. It's going to be equal to 0 or not. If it is 0 in the next row, then we need to go to the next row once again. We need to go to the next row once again. We need to keep on doing like this, and we need to keep on interchanging. So the interchanging essentially needs to be done. That's one problem. So we need to interchange the rows. Okay, that's essentially required. Interchange the rows, and after that only we need to carry. After that only we can carry out this multiplication by 1 by absolute value. So the first thing we need to check is if ABII is 0 or not. If ABII equal to 0. So what is it that we need to do? So we need to go through all the next rows, and so previous rows we should not touch, because previous rows we may have already handled. So we should not touch previous rows. Only the rows from that point onwards we need to check. So what should we do? For J in. So we need to check two times, because it can happen that at no row we are getting it to be equal to non-zero. Okay, that's also possible. J in range from the next row onwards, I plus 1 to where next row onwards we need to choose two rows. So we are checking for non-zero element. If so, what should we check? The corresponding in the entry just below that. Entry just below that means the column is unchanged, but the row is changing. Row is J. Row is J. So where should we give the row? This is the row. If this is not equal to 0, suppose that we are going to suppose that the first row is equal to 0. For example, suppose that we are getting this to be equal to, suppose that we are taking this to be equal to 0.0, suppose. So in that case, we need to interchange the this particular row. We should try to interchange this particular row with the next row. So ABJI not equal to 0, we are going to interchange. So how do we interchange? The rows needs to be interchanged. So for interchanging the rows, AB, which row we should take? ABI and ABJ should become ABJ and ABI. Okay. So after that, what should we do? Once you find a once you achieve this interchanging, you should break this for loop J in range I plus 1 rows, because you need to go down further. You don't have to remain in this particular for loop. You need to break it. If this is happening, but if this is not happening, then what? If this is not happening means what? No, not happening means that you are unable to interchange. You are not able to do anything. So in such a case, it essentially means that you don't have any other rows to solve. Okay, you don't have any other rows to solve. So in such a situation, else means that this break is not happening. The interchanging and break is not happening. Else, what you should do? You should come out of the entire for loop. The entire for loop means you are going to issue a break inside this for loop. So break. There is no more solutions possible. That's it. No more computations are possible here. So whatever you have found, be happy with that. So breaking this main for loop, the final AB will be printed in that case. Let's try to see. There is some error. What is that? Invalid J in range. What is the error here? Equal to 0. Is there any indentation error? I plus 1 rows. ABII equal to 0 for J in range I plus 1 rows. So what's the problem here? Okay, I don't know if that bracket was the problem. Okay, let us try. Suppose that we change it entirely. 0, 0, 0. It's still working. So this is the full general program that we can have. Okay, that's it. So see that in the last case, what happened is that we have 1 minus 2, 1 equal to 8. This is actually inconsistent, right? Because we have here 17. So that we have to make out from this. So if you do not use the entire thing to be 0, then you get 1 minus 2, 1, 8, and 3 and 9, 0, 0, 0, 3 and 9. But here there should have been actually one interchanging. But why is that not happening? Let's just see. Let us see AB in print after each and every step. 0, minus 2, 1, 1. After that, some interchanging is happening. So what type of interchanging is happening? So 2, 4, 1 minus 2, 1 minus 2. So this is not getting interchanged, but why is that? I think in the second step it's happening like this. So in the third step, if AB Ji not equal to 0, ABI equal to, so the interchanging is happening. ABI equal to ABJ, ABI. So and breaking. So the interchanging is not happening in this case. But why is it like that? Let me just see. 0 minus 2, 1, 1. That's fine. So is there any need of giving point 0 even here? That's not the thing. So what is happening at each and every step? Okay, let us see. Going to interchange. Let us give a message also. I'm going to interchange and a new line. So when is it going to interchange? 1 minus 2, 1, 8, 0, 0, 0, 0, 0, 0, 3, 9. So what's happening after that? At this stage, what is the value of I? I value is 1, which means that it's the second row. So J in range I plus 1. I is 1. I is 1 means this is 2. Oh, maybe we should take plus 1. I think that's. No, 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 that's also not working. So what should be interchange? 1 is here, 1 minus 2, 1, 8 is here, 0, 0. So we wanted this 0, 0. So ABI. ABI should be, what is J? So just below that. Just below that means in the same column. Oh, sorry, sorry. In the same, not in the same. Okay, how do we get the same column? Here we have ABII. Okay, that column is going to be I anyway. So ABJI. So ABJI not equal to 0. Let's see what this ABJI is and what this I and what this JR. Let's see everything. I, J, Let us give I and j, or j and I. It's 1 0. If AB10 is not equal to 0, what is AB10? AB10 is this. So that's not happening. After that, what happens? This is 0. J is 1. Next value of j will become equal to 2. So 2 1. Oh, okay. So we are not going into check the next number, right? So we need to go to the next variable that we are not doing here. So it is only looking for the first variable, and we are not going in to look for the next one. So in such a case, what we should do is that instead of breaking, suppose that this particular column you are not getting anything, you should go for the next row, right? We should go for the next row, and we should forcefully interchange, right? This row should be actually interchanged with this row. We have not done that. See, I'll explain what exactly happened here. See here, it located this particular 0 and it's reporting that it's 0. After that, it's looking for a non-zero element here. That's it. It's not finding a non-zero element here, and therefore it's stopping. But what we actually wanted is, we wanted to see if this row contains a non-zero element or not. Okay, if this row contains a non-zero element or not. If this row contains a non-zero element, um, okay, that is not actually the correct logic. So what is the logic that we have to apply there? That's what I'm thinking. So in the first row, in the second row, we have 0 0 0 0, everything 0. So why did that happen like that? Maybe we can. So second row itself became completely 0. So we should essentially check that if the second row is becoming essentially 0. If all the elements in that row is 0, we need to definitely interchange with the next row. So this problem we have not addressed. So if the second row is completely 0, the corresponding entry we have checked. So if that entire row is 0, we should actually, without waiting for anything, we should interchange with the next row. Okay, if that entire row is 0, we should definitely interchange. There is no other way. So how do we check if the entire row is 0? Okay, let us see. Okay, so for that, what we need to do is, so let us do the interchanging in the beginning itself instead of waiting for anything else. So let us interchange if the entire row is 0. So that is the essential thing. That is the first thing that we have to check. If np, the entire row is 0, that's what we are going to check. Np dot all. So what is this array? This array is nothing but the entire row, everything in this row. So how do we take the row? Make the column to be equal to np all equal to 0. Okay, in such a situation, we need to let us change. Okay, let us change it with what? Let us bring the non-zero. Let us bring one of the non-zero row. But in that situation, the problem is that we need to again, if we need to locate the non-zero, that's essentially the difficulty. Okay, the next row also can be equally zero. That problem is there. Next row also can be equally zero. So for so otherwise, what we can do is that we can interchange with the I plus one row, and now the I plus one row is in the ith row. Since the I plus one row is in the ith row, what we can do is that now I has become one more. So reduce I by one and again continue so that we can repeat this process. I think that's the only way. I'm not finding any other better logic. So let us just interchange with I plus one row. This should become equal to I plus I becomes I plus one, and I plus one becomes equal to I, and reduce the value of I by one so that we can again check if this row is also zero or not. But will it go into an infinite loop? That's another problem. And if the row is not the last row, that also we should check, because if it's the last row, there is no point in checking. Already it has become everything zero. No need to check anything further. Let us stop. So, and I not equal to what is the last row? Rows minus one. Okay, the feedback form. Let me just copy and paste it into. So the logic is here. If you are the last row and everything is zero, there is no need to do anything else. Just stop. Okay. So go down and break if you are not finding anything. That's it. So if you are not at the last row, then try to interchange and reduce the I to again recheck that by reducing the value of 5 by 1. So for example, suppose that we are in the second row. Suppose that we are in the second row. Suppose that we get it to be equal to 0. So we are interchanging second and third rows. Now the problem is that we need to check the third row is now in the second row position. We need to again check this third row. So sorry, second row. So for checking the second row, but the problem now is that I has now become equal to 3. But reduce I by 1 and again go back. Do this check once again. So I minus equal to 1 and continue. I think this should work, but I'm not very sure about that. Let's try. Still there is no success. I don't know whether we will be able to solve this issue by writing a simple code. I will try to find out that if it is possible to just okay, what is happening here? If NP all in that particular row is equal to 0 and I is not equal to rows minus 1, that is I is not the row number 2. So I and I plus 1 should be interchanged and I should be reduced by 1. So what will happen at this particular stage? 1 minus 2, 0, 5, 0, 0, 0, 0, 0, 0. Okay, there is one problem that the last coefficient we are anyway not going to consider. The last entry in that particular row is actually corresponds to that right set constant. We are not interested in that. Therefore, we should not do entirely like that. But instead of that, you should reduce the column by 1. So up to where we should do, not all, 0 to column minus 1. Columns, sorry. Still there is no luck. 1 minus 2. So if everything is 0, so what might be happening here? Let us try to see it. Try to do a print once again. With the message interchanging. interchanging what and what, interchanging these two. So interchanging 0, 0, 0. But is it really happening? API. So how do we swap? That's a question. Okay. Uh, is 0, 2, 2, 0. I think this is not necessary. Let us try to do the swapping is not actually working. X and Y. X, Y is equal to Y. It's okay. This command is probably wrong. Let me try to fix that. Trying to fix it. So how do I fix that? A, B. I think the command is slightly wrong, which I used. So the ith and j. Okay, I don't know. I am just copying from internet. Stack exchange. That is correct. Will just try to see j and I. I'm not very sure about this. Okay, it seems that it's working. So this is how the swapping is working. So essentially, the this notation actually stands for this notation. This stands for this is equal to ij colon this. This is the meaning of this. So this is the way to do that. Okay, so this is being done. Now it seems to be somewhat okay. So 1 minus 2, 1, 8, 0, 0, 3, 9. So the solution is therefore x3 is going to be equal to 3, and we are getting x1 and x2 we are getting to be dependent. So that's it. So I think let me just update the entire thing into the Google document. Update. So with this probably I'm stopping. If there are any questions, you may please ask now. Any clarifications required? So I wanted to just complete the LU decomposition also. So the topics that I wanted to complete as a part of this workshop finally are the following: that LU decomposition I wanted to do, and Newton some numerical integration also. But since we have already seen the numerical that what do you call how to deal with numpy and how to deal with so solving this equation using Newton-Raphson method and all these things. So numerical integration is nothing but just applying a formula. So it should not be that difficult once you understand the theory behind numerical integration. So numerical integration can actually be easily understood, and LU decomposition also can be not very difficult to understand once you understood this Gaussian elimination method. But maybe if you feel like we should explain this LU decomposition, we can probably do that tomorrow. Or otherwise, what we can do tomorrow is to give a brief introduction to the SageMath software, which is actually based on the Python software. Okay. So all types of all the commands that we have discussed so far in the Python sessions can be actually easily carried out in this SageMath. Plus, in addition, a lot of extra libraries are available in SageMath software, which is actually one of the most robust mathematical computation system, which is open source available these days. So I am leaving it to you to determine, to decide whether we should go into LU decomposition and Newton numerical integration part, or we should go into a brief introduction. I cannot explain too much about SageMath software because that itself is a full course. So I can try to give you a brief introduction into that. So maybe you can decide. If you can let me know, I can try to arrange the presentation that way. So, so what is your opinion? What do you think? Sage math or LU decomposition using Python plus numerical integration? Okay, one suggestion is LU decomposition. Anybody else? Okay, LU decomposition seems to be somewhat more useful for many of them. So I will go into LU decomposition, but I'm not anyway planning to go into Newton, the numerical integration. Numerical integration is quite easy, not very. So Simpson's rule is there, and such rules are there, and they are just formula. Once you know how to handle this Python commands in numerical Python and all, handling such formula is not very difficult. But LU decomposition I can try to explain. So LU decomposition is what we are going to discuss tomorrow. And after that, if time permits, we will go into discussing something related to Sage Math or something, some general questions can be asked and I can try to clarify. So if there is anything else, any other clarification required, any questions are there, you may please ask now. Or otherwise, we will stop and we will wind up today's session.
If there are no questions, we can wind up today's session. Thank you, Vishnu sir, and thank you all. We can meet tomorrow.
At 6 o'clock, right, sir?
Okay.
Okay. Thank you. Thank you very much.